Good morning, everybody. My name is Valerio Setti, and today I'm going to present to you this talk about the cryptography support in Zephyr, in particular focusing on what happened recently in this area and what to expect for the near future. First, a bit of introduction. I work for BayLibre, which is a consultancy company based on southern France in the Nice area, which is working on all the things related to embedded devices such as Linux kernel, Yocto, U-boot, Zephyr, of course, and recently also GNU compiler and toolchains. I joined the company back in 2022, and since then I've been mostly contributing to Mbed TLS, but also had the chance to play a bit with Zephyr, of course. And for your information, I'm also the company's representative in the Zephyr TSC. Here's the agenda of the talk. We'll start from a bit of a background for the crypto area in Zephyr, then we'll focus on the reason for which TinyCrypt was deprecated last year, then we'll move toward Mbed TLS first, and trusted Firmware-M later. Then we'll have a section about the challenges we faced when we tried to deprecate TinyCrypt in favor of PSA Crypto APIs, and finally, the future steps on the crypto area. So back when I started contributing to the crypto topics in Zephyr, so the first half of the last year, there were 3 different crypto providers back then: TinyCrypt, Mbed TLS, and trusted Firmware-M, also known as TFM. Each of these libraries is providing crypto support by means of their own APIs, and due to subsystem dependencies, it could have happen that you have more than one library being enabled at the same time in your build, which is not great because you're going to duplicate the crypto support there, right, to take extra footprint. But at the time, though, luckily, the security working group already had planned to transition toward a unified interface, which is the PSA Crypto API 1. So what does PSA Crypto API stands for? Well, it's Platform Security Architecture, and it's a set of API who has been proposed, and it's also maintained by ARM. And the idea is that if you implement this set of API, you can get all you need for your device to be secure, especially for your IoT device to be secure. So it's just not limited to crypto. It includes also attestation, secure storage, firmware update, and device status. Then let's see the reason for which TinyCrypt was deprecated. Well, first of all, the project was no more maintained upstream, meaning that in case of any security issues, Zephyr had to come up with its own fixes. And secondly, the library was not implementing the PSA API interface that we just saw, so it was not adhering to the long-term plan of the security working group. From a functionality point of view, then, the library had a limited support for crypto algorithm, which was barely okay for the Bluetooth protocol, but not enough for other protocols such as TLS, OpenThread, and others. It also lacked any mechanism for key management, both at runtime and at rest. So the end user had to deal with the key material directly and handle and store that some way. So, and this result in, the final result could depend on the final user knowledge and experience on the topic to get for the final performance and security. So basically, the only advantage of using this library was the fact that it was tiny. So it has very limited ROM and RAM footprint. Minor note, the deprecation happened in a couple of steps because it was extensively used on the Bluetooth protocol. So the Bluetooth group wanted the end user to give the end user some time to transition toward the new solution, which is PSA APIs. This deprecation left us with only 2 providers for crypto support: Mbed TLS, especially through its legacy interface, and we'll see in a moment what this legacy means here, and the PSA Crypto API 1. So, but PSA APIs, as we just saw, it's just an interface. So who is providing that in Zephyr? Well, we have 2 different providers: Mbed TLS, again, or TFM, which under the hood uses, again, Mbed TLS to provide the crypto support. So since Mbed TLS seems to be used in a lot of places in Zephyr, it's worth to give it a better look. The project was initially named PolarSSL, and it has been later renamed to Mbed TLS once it was acquired by ARM. And its latest official release is the 3.6.4, which is an LTS one, and it has been integrated currently in the Zephyr LTS as well in the main branch. From an overall point of view, it's a full TLS stack library, meaning that it provides you all the things you need to implement a TLS connection from the TLS protocol down to the crypto support. It's an open source project, and it has been used in a variety of other projects, from very embedded ones, such as Zephyr or LWAP, up to standard PC, like Debian packages, curl Linux tool, and others. The library itself is extensively tested, first through their internal CI, which validates every contribution that it's done at the library, third-party assessment that happen from time to time, and also by the fact that TFM is a certified product. So since Mbed TLS is used there, it gets indirectly certified through that process. The project also files and resolves security advisory and CVE. So here's the link in case you're curious to check them out. And the list is, of course, updated at every release. From the software point of view, the sources of the library can be split into 3 different layers. You have the top one with TLS NX509, some intermediate with PK MDM Cipher, which acts as a wrapper to the low-level crypto, which is, of course, the third part. Each of these layers have its own, their own public APIs. So your Zephyr application can basically link to any of these, of course, depending on what your application needs. As you might guess, the TLS part on the top layer implements the TLS protocol. So in practice means TLS and TLS 1.2 and TLS 1.3, whereas the X509 part implements all the stuff you need for certificates management. Currently, there is no alternative in Zephyr for this kind of support for TLS. So if your application needs or will to perform a TLS connection, it needs Mbed TLS in the build. And that's the entry point, for example, for socket TLS in Zephyr. The intermediate layer, as I mentioned, acts as a wrapper to the low-level crypto. And here you have MD for hash algorithms, Cipher, of course, for block cipher and EADs, whereas PK for asymmetric keys, RSA, and elliptic curves ones. The question from the Zephyr point of view might be, do I need them in my application? Well, if you're going to use TLS, the answer is yes, because the top layer makes direct call to the wrappers, so you cannot get rid of that. But if you're just going to use the low-level crypto, then as for MD and Cipher, it's better for you not to make use of them, because it's better to go direct access to the low-level crypto, because they just add extra code, so extra footprint. Whereas for PK, it's a bit of a different story, because in that case, it adds some handy functionalities for reading and parsing keys. So yeah, depending on your needs, you might still depend on that or need that. Of course, low-level crypto is where all the crypto algorithms are implemented. But this is done by means of 2 different interfaces. You can either go the legacy interface, where it's the software implementation and namespace for function starts with Mbed TLS _module _ functionality, or the PSA Crypto interface one. And minor note and spoiler, this interface is named legacy because it's going to be removed on the next release, but we'll see more on this later. Actually, the PSA Crypto part does not just implement crypto support, but it also adds some other functionalities, a couple of them, functionalities which are very handy. First, key management, so that once the key is imported inside the core, the user doesn't need to care about the key material anymore. It can just reference the key through its ID, which is handy. And it also allows to dispatch key storing, so on non-volatile memories, to PSA ITS, internal trusted storage, in case you have that available. Because Mbed TLS out of the box doesn't have an implementation for that, but if you have that, and we'll see how Zephyr addresses this later, you can store those keys there. The second part done by the crypto core is driver dispatching. So looking for an implementation for the algorithm. And this can either go the built-in driver solution, where driver is still a software solution that implements the algorithm, and that's where legacy module still lives. So they're removed from the public interface, but they're just kept there. Or the external driver, and that's not provided by Mbed TLS, because the idea is that vendor need to provide this part, because every SoC, every CPU has their own accelerators in hardware. So it's vendor that need to implement this part. So Mbed TLS just provide calls for that, and we'll see how to address this later. For those familiar with Mbed TLS for some time now, they might also be aware that there exists a build symbol by the name Mbed TLS and something alt, which allows vendor to provide support for their hardware also in legacy modules. This is available up to the latest LTS release, and it will stay there. But this slide is mostly to warn you that this mechanism is going to be removed starting from the next release in favor of the PSA Crypto driver interface, and we'll see more details on this again later. So here's the picture of Mbed TLS on the overall picture of Mbed TLS we just presented. So from the build configuration point of view, Mbed TLS is built starting from a configuration header file, which allows you to select all the features you want in your build and with a fine-grained capability tweak all their internal mechanisms. Here's the configuration header file, the default one that's used in Zephyr for building Mbed TLS, together with the corresponding kconfig that sets build symbols here. There's a couple of limitations here that have to be taken into account. First being that, unfortunately, the configuration header file nowadays does not include all the build symbols that are known to Mbed TLS. And the second is that there is no one-to-one mapping between kconfig and build symbols, meaning that it can happen that a single kconfig enables more than one build symbol. And both things would be nice to have fixed in the future. But now, let's move to the second PSA API provider in Zephyr, Trusted Firmware-M. TFM does not only, as I mentioned, implement crypto, but it implements all the PSA API that we saw initially. And as I already said, it uses Mbed TLS under the hood to provide the crypto support. It's worth to notice that it's actually not the stock version, the official version of Mbed TLS, because the TFM team add some few patches on top of that. The reason for this is simple. We just saw that Mbed TLS allows vendor to provide support for their hardware, their accelerators. And we know that modern ARM SoCs integrate hardware accelerators for crypto operations, like the crypto cell, or key management units. And since TFM is owned by ARM, it goes without saying that they're adding these patches to add support for this kind of stuff in new ARM SoCs. Then from the functional point of view, it's important to notice that TFM only provides crypto support, so no TLS NX509. So if your application is willing to perform a TLS connection, you're going still to need the TLS protocol to be provided by Mbed TLS, and only the crypto part will be provided by TFM. Let's see how TFM is more secure than Mbed TLS. This is based on a feature on new ARM SoC called Trust Zone. And the idea is, in short, that the CPU have a new possible state, which can now execute either non-secure or a secure state. And there's a clear separation between the two, so that when executing on the non-secure side, you don't have access on what's on RAM and ROM on the other side. So, of course, here, Zephyr lives, same color, on the non-secure side, and TFM lives on the secure side. So whenever Zephyr needs to perform any PSA API call, there is a transition between non-secure world to the secure one, where the operation is actually performed, and then the result is returned back to the non-secure side. Now let's go through a quick comparison between the two solutions in terms of crypto support. First, availability on platform. Well, Mbed TLS is a C library, so you can build that on any platform supported by Zephyr. Whereas the same is not true for TFM, because as we just said, it's only supported on CPUs which implement Trust Zone, which means CPUs implementing the ARM v8 or 8.1 architecture, such as Cortex M33 and similars. In terms of flash requirement, then, the Mbed TLS takes more space as more features have enabled in that build. And again, the same is not true with TFM, because once you enable TFM, you have your flash memory will get partitioned in order to have to give all the services provided by TFM the possibility to work properly. But let's go to an example to give you a better explanation. Here I took the NRF5340DK, which is a development kit from Nordic, where the SoC has 1 MB of flash. On the left, you see that if you build an application with TFM disabled, the Zephyr application takes, of course, the entire megabyte of flash. On the right side, you have the same application built with TFM enabled. And as you can see, your flash will get partitioned in a way to get all the services the possibility to work properly, like protected storage, internet trusted storage, firmware updates. So long story short, your space for your application, Zephyr application, will get shrink down to 192K. So, but of course, there are pros in enabling TFM, and that's the improved security. So in terms of, for example, credential accessibility at runtime, with Mbed TLS, you have everything which lives on the same side of your Zephyr application. If your code have any bug for which an attacker manages to dump part of the RAM content, yeah, credentials are there. So they might manage to get access to your credential as well, which is not great. The same, as we saw, cannot happen with trust zone because there is separation. So if you have a bug on the non-secure side, it's very hard that they can manage to have access on what's on the secure side where credentials are. Also, for what relates to credential storage at rest, as we said, Mbed TLS unfortunately does not have any mechanism to store keys on non-volatile memories out of the box, whereas TFM does. So the end user doesn't need to take care of that directly. Fortunately, though, secure storage have been introduced for this recently in Zephyr, and the idea is that secure storage provides an implementation for PSA ITS in case your device doesn't have TFM available. And that's a great combination because together with Mbed TLS, it allows you to have a unified interface so you can have the same function and same behavior that as you would have with the full TFM implementation, but just using Mbed TLS and secure storage together. So at least you can store keys in a quite secure way. From a build configuration point of view, then TFM is built using CMake, and all the key configs from Zephyr are passed down to that CMake build. As we already mentioned a few times, Mbed TLS is being used under the hood also in TFM to provide crypto support, but in this case, the end user won't have a fine-grained way or capability to configure the features there, because the TFM team only allowed profiles, and 4 of them to be set by the end user from small to large. And the idea is that the bigger the profile you pick, the higher amount of services, security, and crypto support you'll get on your TFM image. So there's a caveat here that has to be noticed. If your Zephyr application is willing to perform a TLS connection, they're going to use TLS provided by Mbed TLS on the non-secure side and TFM for the crypto support. But as we mentioned, the first is built using a configuration header file, whereas the latter is built using a profile. And what can happen is that on the non-secure side, you're willing to select a key exchange or encryption algorithm that fits your server connection. And you forgot, for some reason, to set the proper profile on TFM. The build will be fine. It will fail at runtime because the non-secure side is going to ask to the secure side TFM to implement an algorithm, crypto algorithm, that's not supported there. And because there is no hardening between the configuration header file set here to the profile set here. And of course, this is a thing that it would be nice to have fixed for the future. Now let's focus on the challenges we had when we tried to deprecate TinyCrypt. Well, TinyCrypt, as I already mentioned, was extensively used in Bluetooth protocol. And some of the devices there were extremely constrained, meaning that TFM was not available, and Mbed TLS was the only PSA API provider possible there. So the challenges we faced were related to 3 different points: footprint, performance, and entropy source selection. For the first 2 points, here I listed the crypto algorithm which are required for the Bluetooth protocol, but without going into the details, we can just say that for most of them, Mbed TLS already had optimization for footprint available. And the only missing part was the optimization for elliptic curve management, especially for the curve that it's highlighted here, which is the only one used in Bluetooth protocol. And again, I want to give you an idea of what I'm talking about. So here's an example that I added to the Zephyr code base, and it's pretty simple, very few lines of code. I generate a couple of elliptic curve keys, and I perform a key agreement between them. So here, down here, you can see a comparison in terms of footprint, done at revision 4.1. Top one is using a TinyCrypt as a provider for the crypto operation, whereas the bottom one is using PSA API provided by Mbed TLS, of course. As you can see, you're moving from 40K to 55.5, which is a great increase for an embedded platform, and of course not great. Well, we already saw part of the reason for this, and it's that the PSA Crypto Core, it's not just the crypto algorithm, but it implements features like key management, driver dispatching, and others. But that's not all. The problem is that Mbed TLS, by default, uses a lot of heap memory, which is a pain for an embedded device. And it has two kind of a problem. First, you need the code from the C library to manage memory allocation and freeing, which you don't have in the case of TinyCrypt. And secondly, if you do multiple heap allocation and freeing at runtime for every computation, it takes time for an embedded device, which is not great. Well, solution to both of these problems came from a couple of fixes added to Mbed TLS last year. The first being to give the possibility to the PSA Crypto Core to store the key material inside the core in pre-allocated static buffer instead of heap allocated ones. And the second being the enablement of what is called the P256M driver, which is a software optimized implementation for the elliptic curve that it is used on the Bluetooth protocol. And among other optimization, the biggest one is also related to the fact that it does not use heap memory. So combination of the two allowed us to get completely rid of heap memory usage, and so smaller footprint, and at the same time, faster execution. So back to the example that we saw initially, we were at 57.5K. Using these couple of fixes, we were able to shrink down to a 41K.5, which is a great improvement. Still a bit larger than the TinyCrypt case. And yeah, that's related to the fact that you're removing heap memory, but you still have all the wrappers, key management and stuff there. So you have to pay some space for that. But it's still much closer than what we had before. So in case you're really looking to get as small as possible, there is a not so suggested or dirty trick that you can make use of, and it's this kconfig up here that allows you to get direct access to the driver and completely bypass the PSA Crypto Core. And in this case, as you can see, you can even get smaller than TinyCrypt case. Well, that's not suggested though, because as I already mentioned, it's bypassing the core, so you don't have any key management out of the box. You need to do that manually. So you fall back to the TinyCrypt case. You're lost all the benefit of using Mbed TLS. And also, that interface for the driver is the internal one inside the Mbed TLS, so it's not granted to be stable over time. So not great idea. The third problem, as I mentioned, is the entropy source selection. And this is related to the fact that PSA Crypto Core always require you to have a valid entropy source in order to initialize property. It doesn't matter which kind of algorithm you're going to use there. So from your SOC point of view, you can basically fall into two different paths. You have the best path, which is the one on the left, where you have the entropy source available, it's enabled, so that Mbed TLS can make use of that. And that's the best because you get a smaller footprint, and at the same time, hardware entropy generator means real secure random data, and so more secure. Or you have the right path, which is the bad one. And you can fall here either if you don't have the hardware accelerator, or, and that's important, you don't have it enabled in your build. In this case, Zephyr can still kind of a fake entropy sources, but it's using a timer for that. So it's not real randomic. So what Mbed TLS needs to add in this case is some crypto magic algorithm to have those data look more randomic, but it's not great for a couple of reasons. First, it's not secure because data is just more randomic, not real random. It's just pseudo-random. So it can be guessed by someone who's trying to attack your device. And secondly, this crypto magic stuff here takes space on your footprint. So not the best option. So the question is, what is preventing my entropy driver for being used by Mbed TLS? Well, It's related to the fact that by default, drivers are disabled on the SoCs, at least most of them. Especially the entropy one have this gating symbol for all the drivers to be set as no. And the reason for this is that if you're building a Hello World application, you don't want all the drivers to be kicked in for no reason to take footprint, memory, power consumption, and time at runtime. So what you need to do is to explicitly set that. So the question might then be, okay, so cannot Mbed TLS simply enable that symbol for me? Yes and no. Yes, and it could work if you have a real entropy hardware possible under the hood to enable. But if you didn't have that kind of support, that enabling this symbol won't solve your problem. And yeah, DCI will complain because there will be failure at build time for missing support. So what we were looking at was an internal mechanism to tell Mbed TLS, hey, you have in the device tree, there seems to be a node which can provide you entropy hardware support. So enable entropy generator so you will be able to make use of that. So that's why I added this internal helper kconfig here. So long story short, all you need to do nowadays is to set the Zephyr chosen property, Zephyr entropy, pointing to your node of the hardware entropy generator, enable Mbed TLS, and it's PSA Crypto core, and out of the box, you'll get entropy generator enabled, so you'll be able to make use of your Mbed TLS, sorry. We'll be able to make use of your hardware generator, so you get higher security and smaller footprint at the same time. Now, a short section about future steps. First, on the Mbed TLS side, on ideally September, but Q4 this year, the next release is expected. And this is going to be a huge breaking change because what was once a single project is now to be split into two different ones. You'll have Mbed TLS on one side, which from the next release will only include TLS and X509. And on the other hand, you will have TF PSA Crypto, which will include all the middle layers and low-level ones. Ideally, the two should be independent in the future, but for the time being, so for the next release, Mbed TLS will still depend a bit on TF PSA Crypto in order to build properly. There's another change among other, which is important to notice here, and it's related to the fact that TLS and X509 will now, by default, assume to use PSA APIs instead of legacy support. And that's exactly the opposite of what happened to the latest release, when by default, both of them were relying on legacy support instead of the PSA one, and you have to enable the PSA explicitly. Of course, it goes without saying that, as you can guess by the name, TF PSA Crypto only exposes PSA APIs. So this means that legacy modules are not just being canceled from the repo, they're just being hidden from the end user, and they're still being used under the hood to provide the software support in case you don't have any hardware accelerators. But hiding them means that all the build symbols related to them are just going to be removed from the configuration header file, so you cannot set them explicitly. And together with them, of course, also the alt symbol that we saw previously. So, as already mentioned, well, the question now might be from a vendor point of view. So, okay, how can I then provide support for my hardware accelerator? Well, the idea, according to the Mbed TLS team, is that you need to transition toward what they call PSA Crypto driver interface. So, how does it work? Well, the idea is pretty simple. You have to provide your driver in terms of either library or C or header file, and together with a JSON file, which describes what your hardware is capable of doing. And Mbed TLS, on their side, they have some Python scripting and a Jinja template. And the two worlds put together at build time, they will generate PSA Crypto driver wrappers, C and header files, that will be used at runtime to dispatch either to your external driver implementation or the built-in solution in case you don't have any implementation supporting that specific algorithm. There's a big warning here, though. it's that this mechanism is not fully developed yet, and it won't be for the next release. But I have been told that it should be completed by Q4, at the end of Q4 this year, or at worst, the Q1 next year. So on the Zephyr side, what we need to do is to prepare for this next Mbed TLS release. So start removing direct usage of legacy crypto in favor of PSA Crypto APIs, removing K-configs related to legacy modules and others and similars. Then once this will be completed, we'll try to improve the coverage and mapping for Mbed TLS build symbols. And last but not least, it would also be nice to find a way, in case you have in a TFM build, to pass build symbol for your TLS configuration down to the TFM build to avoid runtime failures that as I discussed previously. So that's it. Thank you for your attention. If there is any question, I'm available. Sure.
Can you share a bit of information about the roadmap for post-quantum?
I think that from the Mbed TLS point of view, at least, they have planned to do that, and that should happen immediately after the 4.0, 1.0 release, because the latest one that we are currently working on, it's mostly to reshape stuff for splitting the two, and as been told, yeah, they should start focusing on that later. I think they had requests for that. There's, as far as I know, no mechanism for that yet there, though. So it will take some time, because there's the team, it's also pretty small. Sure.
Is there a noticeable performance overhead when using TFM as a PSA crypto provider instead of the Mbed TLS?
Actually, I've never, I've never tried around. Of course, you have the transition from the two worlds, so you have to what's on the non-secure side, you have to switch there. Part of it, I think it's just a couple of calls, because you have to the gateways which are in the middle, so the first call, and then you have the other to the secure side. So I don't think it's super. It takes too much compared to the, especially since TFM can have accelerators for that. If instead you're staying on Mbed TLS side only, you might fall into just having the software support, unless you have some hardware explicit enable for that.
Yes, that may outweigh like the disadvantage of the context switch every time you're.
Yeah, that might be a decent plus, especially for some algorithm, like if you try to do stuff with like an RSA key and you go 4,000 bits, it takes time on an embedded device. You can really see that.
The idea of this crypto API, what was it called? This PSA Crypto API, the idea to be then exchangeable implementation like other crypto.
Yeah, I know for sure that there are other implementations. So Mbed TLS is currently the only non-TFM solution available in Zephyr, but yeah, the interface is public, so you can come up with, and I'm sure there are companies implementing that, because I know vendors that have that.
Yeah, but Mbed TLS is currently the only one having that.
Yeah, currently, yes. Yeah, that's the only. And they're kind of tightly coupled with TFM actually. So in case Mbed TLS or you have a change in the API specs for some reason, yeah, the interface itself, usually Mbed TLS and TFM are pretty aligned, so a vendor might to align as a external. So it might be easier for them, but yeah, you can come up with any PSA API provider there. The idea is to be interchangeable. That's one of the pros. Whereas if you just stick to Mbed TLS calling functionality, yeah, you're limited to those ones. Device tree. As far as I know, there is no plan for that at all, and I don't think it will happen. I think it would be already a good step to have kconfigs. we, yeah, even on TFM, I think like kconfig are not fully supported. Currently, they have built passed down with CMake option stuff. They have some sort of kconfig capabilities. I don't know how much that is supported as well. Yeah, but having crypto partition is like kind of mean that you need to have also the implementation to store that, and Mbed TLS does not have one. We only have one implementation for ITS, and it's storing on files, but just for their internal testing, so it's not really usable anywhere. But if you use secure storage for that, that's really the goal for it. It's meant to be used together with Mbed TLS in case you don't have TFM. And the purpose is that you have your key being stored on volatile memory on your flash, which is described at the device tree. I mean, so it's not flash memory, it's storing capability of, okay. Yeah, for that one, you need the PSA driver interface to have the dispatcher to call your implementation for that. Yeah, I don't. I don't think they'll go. Yeah, because I'm external to them, but I just work with them. But as far as I know, there is no plan for that. Yeah, the secure side actually have services. So I think they have, I haven't really dig into the details, but I think they have a sort of, yeah, it depends on how much complex you want your build to be on TFM side, but because in the simplest case, it's just direct call to the PSA support you're looking for and getting the result back. In the most secure implementation, you have services. So you get the call from the non-secure side, and then you dispatch to your service. So you have, I think they have some sort of internal OS there, very minimal one, I assume. Yeah, it's. Yeah, I think they have some sort of, as I mentioned, OS or dispatcher there. I don't know how complex it is though, but it's not Zephyr for sure. It's their own solution. And I don't think they're even going to move to Zephyr for that. Yeah, as far as I know, at least they're not planning. That's another thing that at least I haven't heard anything about trying to use Zephyr. They were, yeah, trying to use Zephyr as a test tool for their CI. That's a different story. But because that's another thing that also in Zephyr we currently have testing for TFM tests done with their OS, not Zephyr itself, so that's another strange thing. But not using Zephyr inside the secure world. For TFA, I just barely know how it works, so I don't know the details. They might have plans for that as well. Sure. You're welcome.
Obviously, heavy ARM involvement on the TFM side, but for non-ARM targets, is really the choice that use Mbed TLS as a PSA crypto provider and sort of that's it? Or do we have options for non-ARM targets that we can use that?
Yeah, as far as I know, there is unfortunately no options. A nice one would be to have the implementation on a different CPU. And in that case, because I think TFM actually, in theory, it allows you to have different CPUs implement, one the secure side and the other all the rest. But as far as I know, there's no implementation for that in Zephyr. At least last time I checked, there is no implementation. Well, if any of you knows differently, please fix what I'm saying. So that would be an improvement, because now currently what you're trying to do is you need to switch to the, so even from the build point of view, I assume you have to set up stuff so that your binaries blob fall into the right places. So you have TFM in a certain place, the security gateways and the non-secure side, and have to be sort of hardly managed to have the hardware be aware of that. But if you move that to an external CPU, that would, I assume, solve your problem. Then the only problem would just be, okay, I can have support for the hardware accelerator or not in the TFM side, but still you have the separation, at least to some extent.